All right, so you see on the screen. Oh, and before I jump in on that recitation video, the very last problem, I put notes in there to make sure that you caught it, but just in case some, you look down, look away when the note pops up. That very last problem, it's a redox problem, and at the very end, one of the waters, I forgot to put the coefficient of 2 in front of it. So I only canceled out one water, but in reality, you can cancel both. If I put the right coefficient in front of it, we would have been able to cancel both of them. But because I didn't, the final equation kind of got screwed up. But I fixed it in the when I was editing it. I fixed that part. So make sure you pay attention to that part, and because it's a problem that you're going to see something similar to on the test. All right. So let's jump in right here. And so today we're going to start talking about what's today? April Fool's Day. Ain't that something? I should post send an announcement to all my classes that I'm retiring today, just to see what will happen. Um, so this is we're going to talk about reaction stoichiometry. So reaction stoichiometry. And again, what is stoichiometry? But the relationships between the substances that are in a reaction, right? So the reactants and the products, if you have A plus B going to C plus D, and you balance it, the coefficients are that the coefficients tell us what the stoichiometric relationship is between them. So it's a quantitative relationship uh, between the substances in a reaction. Quantitative. Come on, Russell. It's Friday. Right. So quantitative relationship between the substances in a reaction. So we're going to be able to talk about stoichiometry with respect to chemical reactions, how to use balance equations to get ratios, and how to perform calculations with different things like mass, like molarity. But everything is going to always come back to one thing, and that's moles, right? So you see here in this diagram, you got moles of A and moles of B. And depending on what the ratio is between them, that's how you interconvert. So for any given chemical reaction, you can interconvert between any of the substances using the stoichiometric ratio, right? We're going to jump right in and do that. And I'll show you like what I mean by that, right? But if you have moles, you can get anything. We've seen that already. If you got moles and you multiply by the molar mass, you can get grams, right? If you multiply moles by molarity, which is, well, you divide molarity by moles, you can get volume because molarity is moles per liter. So if you remember these relationships, not that, moles per liter, right? If you want to solve for moles, you'll have to divide by the number of moles by the molarity to get the volume, right? Density is what? Mass over volume. So if you know the mass, you know the density, you can get the volume, right? If you want to know how many particles or how many molecules or how many whatever, then you use Avogadro's number, right? This is all stuff we've done. We just never seen it displayed in a diagram form like this, right? So this is the moles. And Avogadro's number is particles per mole. Hey, Caleb. Sorry about that. So this is particles per mole, right? For Avogadro's number. And it's the same whether you got moles of A, moles of B, it's the same relationships. But the point is, we learned this from the very beginning about relationships and how to manipulate them. That's one of the things I've been focusing and stressing, is that any relationship between two things can be manipulated if you have one and some type of conversion factor, right? So we're gonna do the same thing with these stoichiometric relationships. If we know the ratio, then we can interconvert between any molecule. So what the key to interconversion is the coefficients. I think even when we first started this section, we started out talking about interconverting and using ratios at the very beginning. All right, give me 1 second. All right, sorry about that. So you got your stoichiometric factor is based on the coefficient. So let me give you an example. So in this example right here, let's say we have nitrogen gas plus hydrogen gas going to NH3. All right. Can we is this balanced? This is the key. This is why we've been doing so much balancing. If the equation is not balanced, your coefficients are going to be off. If your coefficients are off, any calculations you do with relation to the coefficients are also going to be off. So is this a balanced equation?
No.
How would you balance it?
Pick which one you want to balance first. And NH3, and then put a 3 in front of the hydrogen.
Somebody been practicing. I like that. So put a 2 here. That'll give us 2 nitrogens and 6 hydrogens. And over here, we got 2 nitrogens. You say put a 3 here. That'll give us 6 hydrogens. Excellent. So now it's balanced. And the balancing is the key to everything. So now we got to ask the question, what do we mean by stoichiometric ratios and stoichiometric relationships? Well, what's the relationship between hydrogen gas and nitrogen gas, right? So we could say that there's a 3-to-1 ratio of H2 to N2. That's the start. This is the stoichiometric ratio. Right? We know that. We talked about this at the very beginning. I think Maya answered that question. It was a couple of weeks ago. But those coefficients tell us everything. You can derive anything from these numbers. Anything with relation to this reaction, you can find out from these numbers. What's the ratio of nitrogen gas to ammonia on the other side?
1 to 2.
1 to 2. That's right. Because this is understood to be 1. Is that right? So it's a 1 to 2 ratio. Right? What's the relationship between hydrogen gas and ammonia? God dang it, Russell, tighten up. H2 to NH3. What's that relationship?
3 to 2.
3 to 2. All right. If you know that, if you have a balanced equation, you can figure out anything relative to that reaction. And you can convert from one substance to the other using that ratio, right? Let's say if I had 10 moles, let me give you this example, and then we're going to do a real example. This is all just me spitballing right now. But what if I had, and again, this is why we started out at the very beginning, learning about conversion factors, how to cancel certain things, what you want to keep versus what you want to get rid of. That's why we learned that strategy early on to apply it now. Nobody tell me my 3 look like a, never mind, I'll fix it. All right, so what if I had 10 moles of H2? And I ask you how much NH3 that will produce. Right? How can we figure that out based on what we these numbers that we have right here? If I wanted to convert moles of H2 into moles of NH3, what would I do? What would you do? What will my the question is, in a more simplified way, is what is the conversion factor to go from H2 to NH3 using the coefficients that we have?
Using multiplication.
Mm-hmm. How would you do it? Couldn't I set it up like this? 10 moles of H2, and I want, if I'm converting this to NH3, I want that in the top. What's the ratio? 2 moles of NH3 to 3 moles of H2. Is that right? Based on these numbers right here. That's my relationship. That's how I convert. So over here, I'm going to say 2 moles of, I need to move that over, of NH3 to 3 moles of H2. Now the moles of H2 are going to cancel. Is that right? Can somebody calculate that for me real quick? What you would get? Because as long as it's balanced, we can answer any question. It doesn't matter if it's given to us in grams. We know how to get from grams to moles. It doesn't matter if it's given to us in molarity, because we know how to get from molarity to moles. As long as we got a volume. Or if we have a mass and a density, we can get to volume and then get to moles. I mean, it doesn't matter. That's why I was saying all the stuff that we're applying now, we've already seen it. Anybody got that calculated yet?
I got 6.66.
Ooh, can we round that up?
What?
6.67. Let's do that. Or 6.7. Let's do that. Let's round it up. So 6.7 moles of NH3. Are y'all following that? All I did was took what I had in the equation and used it to convert one thing into the other. That's all stoichiometry is. Taking what you have and trying to find out the relationship between what you have. That's it. Like, okay, so let me ask you this. How many grams of NH3 is that? If I get 6.7 moles of NH3 from 10 moles of H2 when I do this reaction, how many grams of NH3 is that? Anybody? How do we get from moles to grams?
Molar mass times moles.
Come on with it. Moles times molar mass. How do we get the molar mass if it's not given?
By adding up what you have as far as the atoms.
Add everything up. Is this new? This is nothing new. We've been doing this forever. Not forever, but for at least for a month. So the molar mass, so to get to grams is what? Moles times molar mass. The moles we already have, 6.7 moles times the molar mass of ammonia, which is 17 grams per mole, right? The moles are going to cancel. I'm left with grams. What do we have? Now, I'm just showing you, like, the reason I'm doing this is because this is all this section is dealing with. It's nothing, it's not some new esoteric part of chemistry that we've never seen. We've seen all of this before. So 6 point, where's my calculator?
I got 113.9. I guess you can round up to 114.
No, we can keep this one. I just didn't want to I don't want to keep the other one though.
See, I be confused on when you're supposed to round and when you just leave it the same.
No, you go round it. I was just joking because you said 6.66. So that's why I was like, nah, we're gonna round that up.
See, yeah, don't confuse me now. Look, I don't know when I'm supposed to do it.
No, it's not about it. I was just being a goofball. But that's okay. We're gonna keep that. We're gonna keep this ideas, right? So that's what I'm saying. This is how these are the calculations we can do, all based off of knowing the ratio of one substance to the other in a reaction, right? So let's do some examples. And this is right. All this is basic, simple calculations. So let me ask the question. If we are doing a reaction, I want you to be balancing this. We're going to balance it first because we never stop balancing. We always want to keep practice with that and never forget. And this is going to be CA3PO4 2 plus H2O. All right, here we go. This is my equation. What kind of reaction do you think this is before we start? Is it a precipitation? And this is all aqueous. That's aqueous. That's aqueous. Is it a precipitation? Is it a redox? Or is it acid base? What is this? This will tell you everything. What is this? Anybody remember?
Phosphoric acid.
Come on. Don't I owe you lunch from the other day?
Yeah, I wasn't gonna say nothing though, but it's okay.
Well, I got you. I'm gonna add a little extra to it. It's phosphoric acid. So if it's an acid, that means that this is what? An acid-base reaction, right? Acids don't just react. Sometimes you might use an acid for a redox every now and then, but the fact that you got on the other side HOH in a classic acid-base reaction, you always produce water, right, plus a salt. This is an acid-base reaction. All right. So now, is that balanced? Let's see. We're gonna have to balance this. Balanced or not?
Not. But then do you pull it all the way apart just because the PO4 is the same like on both sides and not the hydrogen?
Yeah, we're gonna keep that. We're gonna keep that intact. That's a good observation. And then what we're gonna do is balance this based on we're gonna keep the PO4 intact. Everything else we'll pull apart. So we got calcium, we have oxygen, which we're gonna count separately. Actually, you know what? Let's do this. Let's keep the OHs intact too. So OH, and then we got H, and then PO4. The reason I say that about that is because we can look at this as one OH group. All right, so over here we got 2 OHs, 1 calcium, 3 hydrogens, and 1 PO4. And over here we have what I got: calcium, OH, H, PO4, calcium, OH, H, PO4. We got 3 calciums. We have 1 OH. We have 2 H's. I'm sorry, no, 1 H, because one of the OHs, one is tied up with OH. 1 H, and then 2 PO4s. What do you want to balance first? I think if we balance the phosphates first, we can figure out the rest. All right. Don't want to do that. Let's balance the phosphate. All right. So we got 2 on the other side. How many, what would you do to this side to make the phosphates equal?
Put a 2 as a coefficient.
Put a 2 as a coefficient here. Right here. Is that right? So that's going to make me have, that's going to be this times 2. So that's going to make me have 6 hydrogens, and this times 2. And 2 there. All right. So now how do I balance that on this side? Now let's balance the hydrogens, because we touched those, so we gotta balance them on the other side. What would you do? Keep in mind that water is 1 hydrogen and 1 OH. So think about it that way. So if I have 1 hydrogen on the other side, what would you do to balance it with the hydrogens on this side?
Put a 6 there.
Let's put a 6 right here. All right, boom, good. So then that means that now we have, this is times 6. So that's 6 hydrogens. OH is also going to be times 6. So now that's 6. The calcium is 3, and the PO4 is 2. So the PO4s are equal. The hydrogens are equal. Now we just need to deal with calcium and oxygen. And look at that. They're both together. And this is an easy fix, isn't it? Because if we want to get 6 OHs and 3 calciums, what would you put there as a coefficient?
3.
We end up balancing both of them at the same time, right? So that's times 3. And this is times 3. Everything is balanced. It's all love, right? So that's the first part. So now it's balanced. Now we can ask this question. And I'm gonna write the question out, because I want you to get used to reading these questions and understand.
I'm sorry, one quick question. So when we had the water, at the top there, where we broke it apart as the H and then the OH, yes, should we just kind of do that all the time, or like kind of assume that it looks that way all the time?
Well, no, we did it because we had an OH group over here.
So if the OH group wasn't on the other side, then we would just keep it all together as water.
Yeah, we could have left it as H and then O. So 2 H's and 1 O. But
okay,
the fact that we had an OH group here, right? That's, again, balancing requires some nuance. And so that's a nuance. Just like when we kept the PO4 together, that's a nuance. Only because it was visible on the other side intact. Right? So the OH, me breaking water up into H and OH, I only did that because the OH was on the other side intact. Right? So that's why I did it. So it's just case by case. There's no general way to do it. Sometimes you're going to leave water intact as H2O. Other times you won't. This is a case where we could look at it as its 2 constituents, because it's literally H plus and OH minus. Right? And then the fact that we had OH minus on the other side, we kept it like it was. Because if we wrote this out in ionic form, because right now it's in molecular form, if we wrote it out in ionic form, you will see that water is H plus and OH minus. And then this calcium phosphate will be Ca2 plus and PO4 minus 3. And then phosphoric acid, if you take it off 1 H, it will be H plus and then H2PO4, like that. And then the calcium hydroxide is Ca2 plus and OH minus 1. So if we wrote it out like that, you would see that. But we didn't, so but we did find out we could keep it. So that's why we did it like that. That's a great question, by the way. All right, so now here's the question. And it might take me up. So how many, excuse my handwriting in advance because I'm trying to write this fast. How many moles of calcium hydroxide are required? And these are the type of questions you answer with stoichiometry. Are required to react with 1.36 moles of phosphoric acid. and we're going to go back and read through this problem. All right, so that's the question. Notice this is not about calcium phosphate, because if it was, we would have had to have a molar amount or at least a mass to work with, but we don't. So this is strictly asking about the relationship between calcium hydroxide and phosphoric acid. But it gave you the moles of phosphoric acid, which means we need to find the number of moles of calcium hydroxide that it would take to react with that number of moles. The way we do it is to first balance the equation. Once we balance it, now what do we have? We have our relationships between everything. So there's 3 parts or 3 moles of, and I say moles in relative terms now because we have specific numbers that we're working with. But there's a 3-to-2 ratio of calcium hydroxide to phosphoric acid. There's a 3-to-6 ratio of calcium hydroxide to water. There's a 3-to-1 ratio of calcium hydroxide to calcium phosphate, and so on and so forth. So what is our relationship that we're going to manipulate here? It's asking us for calcium hydroxide. It's giving us phosphoric acid, right? So we're going to take what we have, generate a conversion factor based on the coefficients, and get what we need. So what number are we going to put in the top? If we're looking for calcium hydroxide, what number are we going to put in the top of that ratio?
Three.
This is what we want. This is what we have. And we just need a conversion factor to go from what we want to what we have, and that's it. So this is what we want, this is what we have. So we need to convert what we have into what we want. So we're going to take the calcium hydroxide and put that in the top of the ratio. So we're going to say 3 moles of calcium hydroxide. This is all relative. We're going to divide that by, well, not divide it, but the bottom part of the ratio is phosphoric acid. So 2 moles phosphoric acid. That's my conversion. And we're going to take that and multiply it by 1.36 moles of phosphoric acid. Everybody following that? Is anybody unclear on that in any way? I had my calculator over here. Hide from it. Right? Everybody okay? All we're doing is a little bit of math. Right? That's it. We ain't even spelling a word out because this is low-level math. This ain't even mathematics. This is multiplying and dividing. So it's going to be 3 times 1.36, right? Divided by 2. Anybody got it?
.04 moles of calcium hydroxide.
Yes. 2.04 moles of calcium hydroxide. So if you have, and let me explain how this works in practical terms. If you're in the lab, right? You in my lab on Tuesdays or Wednesdays or whatever, and we're making calcium phosphate, right? So you got calcium hydroxide and you dissolve it up in phosphoric acid, right? It's all aqueous, and you react these two together to get out calcium phosphate, right? And when you get that calcium phosphate, that's the amount that you get is going to be determined by either the amount of calcium hydroxide we start with or the phosphoric acid that we start with. But it's telling us that we're going to start with 1.36 moles of phosphoric acid. All right, let me extend the question. How many moles of calcium phosphate do we get from 1.36 moles of phosphoric acid? So we're going to ask that question. Right? How many moles do we get of product, calcium phosphate? What do we need? This is what we have. This is what we want. How do we get to it? Based on the information we already have here in front of us. I want to go from phosphoric acid to calcium phosphate. How do I set that up?
Put the moles of phosphate. I don't know.
Yes, you do. Yes, you do. Always what you want is always
over what you have.
Yes, what you want divided by what you want to get rid of.
So you just put the calcium phosphate on the bottom.
On the top.
On the top. Okay, because that's what you want.
That's what you want to keep. What you want to get rid of, you put it in the bottom if you're making a conversion factor. So the ratio here of calcium phosphate to phosphoric acid is 1 to 2. Right. So I'm going to use that down here. I'm going to say 1 mole of calcium phosphate over 2 moles phosphoric acid times 1.36 moles of phosphoric acid. Right? So I'm trying to get rid of phosphoric acid and solve for calcium phosphate. So this is how I do it. Right? So that's just going to be what? 1.36 divided by 2. Right? So when I use this amount of phosphoric acid, I'm going to generate this amount of calcium phosphate. Any questions? Anybody not following? Say something. Right? So that's what we're doing. We're taking these relationships and manipulating them. That's it. Right? Let's do another one, but we're not going to solve for moles this time. We're going to bring in another relationship, which is particles, molecules. So let's do another question. If there are no questions about this one. Right, we actually got time to do 2 more questions, and that's great because I only got 2 more questions in my notes anyway. So here's the equation. So ammonium sulfate plus calcium hydroxide gives me balance. I want us to balance it together. NH3 plus calcium sulfate plus water. All right. Let's balance this. And here, the only thing that's intact is the sulfate on both sides. And I think we can do the same little trick we did with water as well on both sides. So let's try that again. All right. And so now let's balance it. So over here we have 2 nitrogens. We have 8 hydrogens. 1 sulfur. Oh, no, let's keep that intact. 1 SO4. 1 calcium. And 2 OHs. All right. On the other side, we got 1 nitrogen, 3 hydrogens, actually 4 hydrogens. 1 calcium, 1 SO4, and 1 OH. Okay. Everybody see that? So 1 nitrogen, 4 hydrogens because it's NH3, and then 1 from the water, so that makes 4. And then 1 calcium, 1 sulfate, and then the OH from the water makes 1 OH. Is that okay?
Yeah.
All right, let's balance the OHs first. Let's do that. Let's balance the OHs first. So we do here, we put a 2 here. Let's see if what that's going to give us. That's going to give us that times 2, and which would be 2. And then for H now it's going to be 3 plus 2, so that's going to be 5. We got 3 here, and now we have 2 here, so that's 5 H's there. And then over here, so now we have 2 OHs and 2 OHs. We have 5 hydrogens here and 8 here. We got 1 nitrogen here and 2 here. So now, since the hydrogens and nitrogens are together, let's see if we could balance the nitrogen, and then see what happens with the hydrogens as well. All right, let's see what we got. So if I want to balance the nitrogens, I can do this. If I put a 2 here, right, that's also going to increase the number of nitrogens. And then this, we have 2 on this side already. So that's going to give me this times 2, which is going to be 2. And now this number is going to change again. So now that's going to become 6. Everybody see that? 2 times 3 is 6. So it's going to change the number of hydrogens again. So that's going to be 6 plus the 2 we got over here, for a total of 8. Right, so now my nitrogens and hydrogens are balanced. Is that right?
Yeah.
And then the calciums are balanced because there's 1 on each side, and the sulfates didn't change, so we're good. So that's how we're going to balance that. So if we were to write this out here, it would just be 2H2O plus calcium sulfate plus 2 NH3, right? So that's that. So it's balanced. So now what we need to do is answer a question. We got a minute. Dog it. That's all right. We can still do it. How many NH3 molecules are produced from 4 moles of calcium hydroxide? Let's see if we can do this real quick, and then we'll end right here. Because calcium hydroxide is one of our reactants, right? Remember, on the left side of the arrow, that's reactants. And when the reactants get together, they produce products. On the other side of the arrow, these are my products. I'm gonna just erase that. All right. So now, here's the question. How many molecules? Notice it didn't say moles, it said molecules. But we need to find moles first, because moles is our central unit. We can go from moles to anything based on molar mass, or molarity or mass or whatever. We can get anything from that. So let's first do, let's look for our ratio. What's the ratio of calcium hydroxide to NH3 in this balanced equation?
One to two.
1 to 2. What do we want to keep? We're looking for what? NH3, right?
Yes.
So we're putting that in the top of our ratio. So 2 moles of NH3 over 1 mole calcium hydroxide times 4 moles of calcium hydroxide. So that's going to be what? 8 moles? Right? Because moles of calcium hydroxide are going to cancel. I'm left with 8 moles of NH3. Now, how do I go from moles to molecules? Help me out. What we have a way to do it directly. Give me what? 8 moles. Times what? Avogadro's number, right? 10 to the 23rd.
I was gonna say that, but I wasn't sure. All right, cool.
Oh, you're right. Molecules per mole. Right? Remember, Avogadro's number is per mole. Particles per mole. You can put anything in the top. The bottom number, the bottom unit is always moles. So we can cancel out moles and get molecules. Right? So 8 times 6.02 is going to be 2.4 times 10 to the 20, let me see, 24th, somewhere up in there. No, let me take it back. 8 times 6 is 48. So we like 4.8 or 4.9 or something like that times 10 to the 24th.
I got 4.82 times 10 to the 24th.
All right, good. But do you see now, and I know we got to go, but do you see how all the relationships we learned early on, all we're doing is manipulating them, moving them around to find what we need. That's it. As long as you understand the relationship between two substances or two things, if you got a way to convert between them, you're good. Or you can use those two things to convert to something else if there's some type of relation between those two things and something else that you want to calculate. All right, so we're going to stop right here. I'm going to upload